Hi everyone. Till now we studied about gradient descent and its different variants till the last video. In this video, we are going to discuss two optimization algorithms which are frequently used in applications. One of them being RMS Prop and the other being Adam. So we will just look into the gradient update rule of RMS Prop and try to map it with the example which we did previously and see how it works. So this is how the RMS prop looks like, and this image is taken exactly from Papers with Code platform, and over there it's clearly mentioned. I tried to find the paper which is associated with it, but it's clearly unpublished and it was proposed by Jeffrey Hinton in one of his lectures in Coursera. And this is how the gradient updation rule is going to look like. Now, there is something which we need to consider over here. The expected value of g is or g square is ideally the running average which we are considering over here. Since we don't have a random variable g square for our applications, we consider this to be as a running average. Now let's simplify the updation rule a bit so that we can actually use it. We say that this running average, which I defined over here, is given by ET. ET is nothing but expected value of g square at time t minus 1, and g square is nothing but the gradient square, which is gradient of L square. That's it. Now we say that the running average ET, because if we look carefully over here, it is ET. We have a gamma as a hyperparameter which Hinton suggested as 0.9. We will use zero point 0.9 only, but for mapping it to a simpler terms, we will write gamma as it is. And if this is ET, this particular term becomes ET. This particular term will become Et minus 1. We write it over here, and then 1 minus gamma will be written as it is, and gt square is exactly what I defined over here, with the fact that if t is there, this is just indexed with t. Now this simplifies the first term. Now for the second term, this is the weight updation rule. Wt plus 1 will be written as it is. Theta is replaced by w in our case. Theta t will become wt, and eta will remain as it is. If we look at this term carefully, this is exactly what we derived over here. This is ET. We write epsilon over here, which is just a term just to make sure that we are not doing a square root over a zero term, and eventually we get a GT term over here. Now if we proceed further with our example, which we had been discussing since last 2-3 classes, this is how it will look like. This is LW, and this GT is pretty much familiar by now. Now we start with W naught as 5, eta as 0.2, and epsilon as 0, and the value of gamma, even though it's not set, it is going to be 0.9 only, as Jeffrey Hinton suggested. Now we proceed with G0. We do it very carefully. Like if I go into the update rule, the first thing we need is to find out GT. We will calculate G0, which is 8 times W0 minus 12. So 8 times 5 minus 12, which is 28. Now G0 square is exactly needed if we have to calculate ET if we look in the example. So we do that and we get 784. Now E0 is the running average of G0 square. Now the running average will mean that we have just one term 784 and we have to find the average of it. So it's 784 only. So E0 is going to be 784. Had there been two terms, we will be adding them and dividing by 2. Had there been 10 terms, we will be adding all the terms and dividing by 10 with respect to the previous average, of course. So we have to find some sort of average over here. But since this is the initializer, we get the value of E0 as 784. Now We start with W1. W1 is W0. Like over here in the updation rule, we put the value of t to be equal to 0. So in LHS we get W1, RHS we get W0, eta is a constant, E0 we have defined in the denominator, epsilon is again some value which is very small, and G0 we have defined. We consider epsilon as of now to be equal to 0 only. Now we proceed further and get the value of W1 as 4.8. On solving we get this. Now we can definitely get the value of G1 from W1 because G1 or GT is equal to 8 times WT minus 12. Now G1 is 8 times W1 minus 12, which will make me get the value of G1 as 26.4 because W1 was 4.8. Now we have finished one iteration. We proceed with other by putting t is equal to 1. On doing so, this is what we will be getting. We will be getting E1 from here. We already have found out E0 in the previous iteration. G1 we were able to find out, and since we have to find out W2, we have found out W1 and also G1 is there. Let's write everything properly for the next step. So this is what we get. And so the value of E1 is derived if we consider this expansion. We put t as 1 over here. The value of gamma is 0.9. I was able to put it over here. E0 will be obtained, and 1 minus gamma G1 square will be obtained. G1 we have derived a step above. This is exactly where we derived G1. The value of gamma and 1 minus gamma is known. E0 was 784, we derived it previously. This is the value of E0 we derived. Now we get the value of E1 as 775.296. Now we do the updation rule. The updation rule will be derived from here. We put t as 1 over here. We get W1, which we mentioned over here. The value of eta was 0.2, which is constant. E1 we just derived. The denominator will be E1, and G1 will be like we derived it previously in the previous step. We solve it, we get the value of W2 as this. Now we move a step further and calculate the value of G2 or the gradient at W2. This is what we are getting. We finish for t is equal to 1 and proceed for t is equal to 2. We do the exact same calculations as we did for t is equal to 2, and on proceeding we first find the value of this running average E2, which is like gamma times E1 plus 1 minus gamma times G2 square, using the formula which we just wrote in the beginning. This is the formula which we are using for ET, and this is actually derived over here only. We were writing the formula, and then on doing so we just apply for W3, and the W3 comes out to be this, and the G3 comes out to be 47.43. Now we can successively keep on iterating for some finite number of iterations, and then we can get the result as we need. Just one thing we need to observe is the fact that the learning rate we considered as 0.2. The good default learning rate as proposed by Hinton is 0.001. So we can try out this learning rate and try to see if we are getting better results with this learning rate or not. Now we will be discussing one of the most important optimizers which we used inherently in a lot of deep learning applications. A lot of transfer learning models have used this Adam optimizer, or at least some variants of this Adam optimizer. Like till now, we have studied some variants of gradient descent. These days, people are studying different variants of this Adam optimizer. This is that important in terms of deep learning applications. So this is just a snippet from the paper explaining the entire algorithm, which I will be explaining with a small numerical example. There is a whole lot of mathematics involved. I will link the paper in the description, and definitely you can have a look. in it. But as of now, we will be just using this algorithm to get a hang of how the optimization algorithm works. Later on, like after 3-4 videos, we will try to debunk the mathematics behind it, just like we did for the gradient descent algorithm. So, um, in this video, I am going to make the updation rule a bit simple for you. This is the entire Adam updation rule. So these are the hyperparameters you need: delta, gamma, and eta, and epsilon. Epsilon is definitely a very small term, just to make sure that the square root is not 0. So these are the hyperparameters we need. If you refer to the paper, which I will be posting in the description, they are using beta 1 and beta 2 in place of delta and gamma. But the algorithm will remain the same, it won't be changing much. So this is the updation rule. We start with some mt minus 1, multiply it with delta, and we get a term like mt. It is very much a term which is dependent on gt. So this is mt, and this is a term which is dependent on gt. What it is exactly, we will come to know once we start solving. We try to find out gt square like we did previously. Gt square is nothing but gt into gt only, and then we do the same updation, gamma times vt minus 1, and what this vt is, we are going to explore once we start solving it. As of now, we are just taking the formula and the corresponding updation rule and try to solve whether we are able to apply an Adam updation rule on a simple problem or not. These terms, both M and V, have their literal meanings when we talk about Adam updation rule. So on doing so, we get the value of m cap t, which is mt upon 1 minus delta raised to power t, and v cap t, which is vt upon 1 minus gamma to the power t. Both of them are having some relationship in terms of unbiased estimators of mt and m cap t. That's why it's written in this way. But as I said, we will be just using the formula, and this is the eventual updation rule which we will be using. Now let's see it with the help of a numerical example. We consider the same example we did previously, and we start with LW, which is the loss function. We know the GT. We start with W0 as 5, or the initial weights as 5. We start with delta and gamma as 0.9 and 0.99. This is actually mentioned in the paper. I think it's mentioned, yeah. So it's mentioned over here that the delta, or in their case beta 1, is 0.9, and gamma, which in their case is beta 2, is 0.999. We use the same value of delta and gamma over here, and we, since it's also mentioned in the algorithm that m0 and v0 should be equal to 0, and they called it as first moment vector and second moment vector in the paper, but as of now we will just treat them as terms which we will just need to calculate. So both m0 and v0 are 0, so will be v0 cap. V0 cap is 1 minus delta to the power t, which will be 0 only, and m0 cap is again 0, and the epsilon, we consider a very small value. We calculate the value of g0 because it will be needed while calculating the further terms, and we also calculate g0 square. This is the w1 which I am getting. So w1 is nothing but w0 minus, just look at this approximation. So w1 is nothing but w0 minus eta times square root of v0 cap plus epsilon, and in the numerator we have m0 cap. On putting or on substituting the values, we are getting the value of w1 as 5, and hence g1 and g0 are both same, because g0 was calculated at w0 being 5. Now if w1 is 5, then g1 will be 8 times 5 minus 12, which is exactly the same value as g0, 28. Now we will move to the next iteration, or even before that, we need to calculate M1 as well. So M1 is the first average, as I said, first moment estimate. So it is del of M0. M0 we estimated as 0, and G1 we just calculated as 28. This value is 0.9 as mentioned in the paper. 1 minus delta will be 0.1 and M1 is 2.8. Consequently, we will follow the same updation rule for V1, the second moment vector, which is gamma times V0 plus 1 minus gamma times G0 square. On doing so, we both get the value of M1 and V1, and eventually we are going to calculate M1 cap. M1 cap is M1 upon 1 minus delta to the power 1. So delta over here was 0.9, power 1 will be 0.9, and we get the value as 28. Likewise, we do it for V1 cap, which is V1 upon 1 minus gamma to the power 1. So we get the value as 784. We proceed further and get the value of W2 by substituting the terms which we have calculated and get the value as 4.8. Using W2, we calculate G2. Now this is a term which is different. I am getting 26.4, and then we proceed to T is equal to 2. We do the calculations again for M2 and V2. We calculate M2 cap, we calculate V2 cap, we calculate W3 and eventually get G3, and we keep on iterating the process till we get a convergence. So that's how the entire Adam optimizer works. So this one was just one small basic example to implement what is there in the paper in just a univariate case. We will be using the same technique if we move to the multivariate scenario, but as of now we will restrict our knowledge to this univariate case so that we know what exactly is happening in the algorithm. Later on in future videos we will be exploring the mathematics behind this algorithm as well. So in this video we covered two commonly used algorithms, RMS Prop and Adam. We saw its application at least in univariate case, which could very well be scaled up to multivariate scenarios as well. In all these optimization algorithms, it is very important to start with a basic example in univariate and then try to see how it works in multivariate and then explore the mathematics behind it. So as of now, we have done the exploration in the univariate scenario completely. Exploration in multivariate scenario won't be that difficult. In some future videos, we will definitely be looking into the mathematics behind the algorithms to make sure how actually they are working and what exactly is prompting them to work in a way which is better than a gradient descent. Thanks for your time.